It's irrelevant either way.
Just pick one and go with it.
It's-
We know what you mean.
It's not okay, so.
Either or. Thank you.
It's for the Adrian monk inside me. All right. Requirement for normal force
Contact.
and requirement for gravitational, let's say specifically generalized gravitational force
True that.
and weight.
One small mass, one huge mass.
And again, huge, we're talking planet, moon, star, something of that size. It's one small mass near one huge mass. And near is relative to the size of the planet or whatever you're dealing with. So if I'm on top of the Empire State Building, that's still near. If you consider the size of the Earth and the size of the Empire State Building, it's really not that far. All right, so for tension, what about the direction of the objects? I've got, if I'm pulling on a rope, pulling on a rope, which way is the tension acting on? So the two objects involved here, besides the rope, I guess we have rope, I have this object, and I have person. Which way does the tension act?
Towards each other.
Yeah. It's pulling up that to the left, so therefore this is being, sorry, if I get my directions correct. The mass is being pulled to the right, the rope's being pulled to the left, and over here. So relative to each other, those forces come in pairs. Oh, wait. Wrong category. This is direction with respect to other force in pair. They point towards each other. What about with respect to the objects?
Along the line of taut rope.
Yeah. So it's parallel to taut rope. Chain, string, whatever it happens to be pulling. What about other? What's the direction of the other force?
Not applicable.
Well, I mean, if I had to put one in there, it does have a direction.
It's problem specific if you give
Yeah.
it.
Problem specific. And then in other words, it is part of a pair, because forces always come in pairs. However, you only draw one, or I should say, draw only one. Because I said it before, I don't really care about the other half of it. Normal force?
Moves away from each other.
All right, so they are opposite each other.
Perpendicular to the surface. Contact.
Surfaces. And you might have put the S in there, I didn't hear it. Normal force, some textbooks will call it a support force, like the Physics 110 book just calls it a support force instead of normal force. For those who have not watched the video, what does normal mean? Normal. Ooh, there's different forces. Yeah.
Okay.
It's called normal force because it means perpendicular. And then gravitational force, what is the direction with respect to the objects? Okay, well, that's towards the other part of the pair, so those are indeed towards each other.
Towards center of mass of the other object.
Yes. And all we left with is friction, in terms of, I have, this slides against the table. Which way is friction acting on the mass container? All right. And so therefore, which way is the force acting on the table? So they are against each other, as all of them are, except they're more sort of parallel, supposing towards each other or away from each other. They're what I generally listed as anti-parallel. All right, about to jump to, instead of going through the progression of simplest to more complex case, I'm going to jump to the more complex case. If you have not watched the videos where I go through the steps to get up to it, you really need to watch those. Questions on what I have on the board right now? I don't think I waited like 3 seconds after asking before I started erasing, so apologies. It's here if you missed it. Insert these to this. Inspired by a MacGyver episode. So basically, the person on the ground is pushing this long pole, as well as pulling on this rope. This person is trying to move off the wall. In the MacGyver episode, the rope didn't exist, but I wanted to throw some tension into it. Physics tension, not emotional tension. Now, on a problem like this would be for test 1B, the last problem, next to last problem, will be something along these lines. one of the problems will be something of this quality. So I asked to do a force diagram. I will break it up for you so that you know which objects I'm dealing with here. Otherwise, if I did not break it up, then it's up to you to guess, are the pulleys, do I treat the pulleys as separate, or do I treat them as part of something else? Am I looking at that pole at the bottom half of the pole, top half of the pole, or is the pole one object? So I draw the objects just so I can make sure I have plenty of room here. Let's see, oh, that's right, the building. All right, so I've got 1, 2, 3, 4, 5, 6, 7, 8 objects. Whenever you're doing a force diagram, let's just start with the checklist. There's my checklist there. We are going to concede here that this is an ideal rope. So I do want to make the pulleys part of the ceiling in that case and the ground in this case. All right. Let's do it. That dramatic pause there is for someone just to name a force acting on which object and in which direction.
Gravity is pulling down on both people on the pole.
I'm going to nitpick that. Spirit of what you're saying, absolutely right, but what is the force? Gravity is not a force. Gravity is a huge topic.
Weight then?
There we go. All right. That is what force due to gravity also would have worked. So we do have weight acting down. All right. Remember, forces come in pairs unless I'm doing other. But we're starting out with the gravitational force or weight acting down. So weight of, I'm going to call this 1. Where's the other part of that pair?
Would it be friction?
The pair, when you're doing a pair of forces, it's got to be the same type. There's going to be another weight, the W1 somewhere.
Can't be pushing up from the ground.
I would debate the word push, but they're being pulled together, pulled on the ground. Based on your hand gesture, you would have drawn it correctly. So they're being attracted to each other. As I jump up into the air and come back down, I first pushed against the earth, so the earth moved away, and then as I came down, the earth came back up. I've done the calculation. If I jumped off the table onto the floor, the earth does move about the distance of the size of a nucleus of an atom. All right. This also had a force acting here. I'm going to cleverly call it W sub 2. What is the other part of that pair? Acting which way?
Up.
Because when the forces come in pairs, the two forces are always in opposite directions on different objects. And then he also said pole, W sub P. And W sub. All right, I think that covers the three that Musa said. Any other weights? Spoil burn alert, yes.
Isn't the rope?
Rope is ideal, so ideal rope is massless and therefore does not have weight. If you did put a weight on the rope, I would not take off for that, just not necessary.
Then it would be the pulleys, wouldn't it? Or no?
The pulleys are part of the ceiling, and this is part of the ground, so I would not treat the pulley as separate. However,
The ceiling?
yes, this whole thing here is being pulled to the ground. If those walls suddenly disappeared, ceilings collapse. So a weight of ceiling, weight of ceiling. Two more pairs to go.
The walls?
Yes. W sub L for left. W sub L. W sub R. W sub R. Now, all those forces that are acting on the ground are really coming, that pull should be, if you went backwards, it should be going towards the center of the earth. I try to put them in relatively even position of where the other counterpart is. So I have W sub P here, so I'll put the other W sub P pretty much below it. Doesn't have to be. Occasionally students will just do a whole bunch of up arrows and label them down here for the other part of the weight. But what physics is claiming here is that there's an attraction there between these two objects. Now, in everyday life, I understand that it doesn't feel like if I jumped off the table, you're not going to feel the Earth move. It doesn't seem like the planet moves, but there's a whole lot that would not be explained if the Earth did not move. Not wanting to shock you, but the Earth is not the center of the universe. Or is it? If you did weights of the pulleys, I would not take off for it, but it's not necessary since I drew the pulley attached to the ceiling. This is all considered to be one object here. Same with the pulley down here. All right, that's it for the weight. That's it for the gravitational force. Put a little check mark next to it. Feeling good. What next? Tension, all right. Which way is tension acting on what?
Pulleys, the rope.
Pulling on the rope, okay. Which way is it acting on the rope?
I guess where he's pulling.
So you sort of did a horizontal motion, so you're talking down here?
Yeah.
All right, so which way is it acting on the rope? So tension is pushing on the rope?
I know.
It's pulling on the rope.
I'm not sure.
Someone want to help them out?
Yeah, it's
It's
pulling.
pulling.
Pulling. Tension's a pulling force. So I have a tension here. And where's the other part of that pair? Yeah, if that rope weren't there, he would not be being pulled backwards. It might be easier for him to move. And likewise, at the other end. I just have one rope, so if you want to do subscripts, these two would have the same subscript, these two would have the same subscript. But with an ideal rope, the tension would be the same throughout. If you flash back to when we did the rope in the hallway exercise, that I commented that the tension in the rope was pretty much the same throughout. Considering the other forces involved, any difference in the tension from here to there, most likely negligible. In 151, we're basically going to maintain that. We do add friction in the middle of the rope at some point. We get the rotational motion, and so the tension might change, but for segments in between the frictions, we're assuming the tension stays the same. In 251, with calculus, you can deal with the fact that as this rope moves, the amount of weight hanging here is going to change, and so that's a calculus-based problem. All right, one rope, we dealt with both ends. Tension, done. What next? We will come back. I'd like to do friction last, if that's okay with you. Okay?
Normal force?
Okay, let's do that one next. Which way is normal force acting on what? On,
All of it, on the people in the pole.
what does normal mean?
Perpendicular.
Perpendicular to what?
Weight.
No.
Surface.
In that case, they wouldn't be acting up or down, it'd be sideways.
Surfaces of contact. So
Yes.
just the man?
All right, so the person's touching two things. The person's touching the pole and touching the ground. So which way from the ground, which way is the normal force? Yeah, there's your up right there. So I have this upward normal force, using 2 there. And the other part of that pair?
Down at the ground.
This normal force down here, this is what would leave